Yeah, okay, great. Hi, thanks for coming. I'm excited to be here. I'm Yarden. I'm a software engineer at Dynatrace, and today I'm going to talk about coding adventure, 7 languages, 7 lessons, and an epic journey. So, like all epic journeys, mine starts at the beginning. And for me, that beginning was 2.5 years ago. Before that, I was a software engineer. I was coding mostly in C. And 2.5 years ago, I joined my current team, which codes in 7 different programming languages. We have 6 different products, each in a different language, and then one has like a little extra language just because why not? You know, if you're doing 6, you might as well do 7. So so when I joined the team, I kind of thought it would be a cool challenge. Um, and I kind of expected that maybe after a year, 2 years, 2.5 years, let's say about now, I would be an expert, a master at all 7 of these programming languages. And, you know, it would be challenging and it would be tough, but I would be, you know, the best Java developer and the best Python developer and the best of everything. And I quickly realized that that's not the case because when you're programming, when you have 7 different projects in different languages, you're jumping between them and you're writing a feature in this language and then this language, you just do what you can to get by. You find the minimum common between these languages and you use that and then you continue on to the next. So what I found out was there was a lot of similarities. It makes sense, right? Programming languages. A lot of similarities between these languages. But what was interesting to me upon reflection a while ago was to see what I had learned from each of these languages. And this talk is based off of those realizations. Because I feel like while these languages are similar, while you can clearly and quickly learn a new language once you have already known one, what's interesting is to see how each language did kind of give me a new perspective and made me a better programmer. So I'm going to start at the beginning, which is C. I'm sorry, by the way, if anyone's thought I would be teaching you 7 speaking languages. It's not in this room. But so in C, I learned that I need to know my software's layers. And what that means is whenever there was an issue in C, I'd have to actually think about these 3 things. So first of all, the most common case is that I wrote a bug. I wrote code, doesn't execute as it should be. That's the most common case. But my code usually calls into libc, the standard library. And so the issue might not be in my code, but it might be when I'm calling into libc. So I'm calling it incorrectly, I'm passing an incorrect parameter, maybe an incorrect type, I don't know, I'm doing something wrong, but it's with the interaction with libc. And then the third layer, if none of these 2 have panned out, then the third layer is syscalls. And syscalls is what the standard library uses to execute code in the kernel. And there may be an issue there. Everything is code eventually. And so I've had issues where the kernel just didn't implement a certain syscall that I was calling, or it was really outdated, just a custom kernel that doesn't do what I expect it to do. And it was really, really important because if I was only stuck on the first layer, the user code layer, which is usually what happens, I would never solve a lot of issues. A lot of issues would remain unsolved. I'd be staring at the same piece of code and not know what's going on. So it's important to know your layers. Now, this was, again, 2.5 years ago. I hadn't thought of this talk. I wasn't even thinking about what I'm learning as I was learning it. But I did realize a while later that I had kept this conclusion to C. And I was coding in Java, or atop the JVM. And what we were coding is a live debugger, which is pretty cool. We can talk about it later, but it's not the point right now. The point is, when you're coding a debugger, you need to know which variables are in scope. And the problem we were having is that some customer was trying to collect a variable in Scala, and the variable was out of scope, so it shouldn't be collecting it, and then there was an exception, and it was crashing. It was terrible. But I didn't think about these layers, and I was staring at my code, and I was like, I don't get it. There's no problem. It was the most simple code, you know? Where does the variable start, and where does it end? And once I know that, I just collect it, or I don't collect it. Super simple. Now, at some point, I was tired of it and I was like, okay, maybe it's Scala's problem. And it was kind of half joke, right? I didn't take myself seriously, but it did end up to be a Scala problem. So what usually happens is the compiler tells me where the variable starts and where it ends. And in this case, Scala was telling me it ended later than it actually did. It was like a super specific case. They fixed it in the next minor version. I wasn't even the one that found this bug. I wasn't the first person that found it, but if I had remembered this, I might have found that a lot faster. So no matter what, know your software's layers. Now, another good lesson from C in general, which still follows me, is to know the internals, or don't be afraid of the internals, is the way I like to phrase it more, because you don't have to know the internals. But I'll give you this example. All my examples are in Java. I think that's pretty neat. But so I had this issue, or not an issue, actually. We wanted to develop a feature where we could have an external logger connected at runtime, and it could not be connected at runtime. And so what I wanted to do is, if we had this external logger, if it existed, we would use it. And if not, we would fall back on a default log handler. So I wrote this xlog handler to use the external logger when it existed, and I wrote this try catch case so that when it didn't exist, it would just fall back to the default log handler. Now, how many of you expect this to work? Interesting. Okay, I did. That's fine. But I expected this to work because I was like, okay, great. We have the import up here. This is the top of the file. The first thing that'll happen is it'll try to import. And when that fails, then I'll catch that exception in the try catch over there, and it'll be fine. But what I found out was that the actual exception would be thrown only when I actually call the log method. So again, if I knew, so what I should have done in this case was I should have took a step back and I should have said, okay, if I want to know when the class is loaded and how it's loaded, I should have read about it. I should have not been scared to know about the JVM and to learn about it a bit more. I should have done my research. I should know the internals, and that would have fixed my problem straight away. So I think we've gone a little bit internal, really into it. So I'm gonna go all the way to like the highest level I'd consider it, which is JavaScript. Now to get into that JavaScript mood, I have some riddles here. So there's two statements here. They're either true or false. So I'm going to ask the first statement, which is 1 is smaller than 2 is smaller than 3. True or false? True? Raise your hand if you think it's true. Okay, great. Yeah. You're right. It's true. Okay, now 3 is bigger than 2 is bigger than 1. Do you think that's true? I don't know what that means, but it's false, okay? It isn't true, and that's weird because obviously we're looking at this, we know that 3 is bigger than 2 is bigger than 1. So in order to solve this, the answer is pretty simple. What happens in JavaScript is that it'll execute from left to right, and it'll only execute like the first operation and turn it into a Boolean, so either true or false, and that will turn into a number because the next operation is also against a number. So what's going to happen here is it's going to say, okay, is 1 less than 2, or is 1 smaller than 2? And the answer is true, and so that turns into a 1. And then is 1 smaller than 3? And the answer is true, so it stays true. The second statement, it'll do, okay, is 3 bigger than 2? And the answer is true, so that's also a 1. But then we get to, is 1 bigger than 1? It's false. Yeah. Okay, are we warmed up? Are we ready for another one? Yeah, okay, let's go. So once again, what's the output of this? We have a string 10 plus 1. Okay, yeah, we get string concatenation. Someone here said that. I'm sorry, it's supposed to be a string. It's supposed to be a string 101. Okay, cool. So that's what JavaScript wants to do. But then what happens when I have a string 10 and I subtract 1? 9, yeah. Great, so I can walk off stage. You already know all the JavaScript that you need to. So this might be counterintuitive, but when I see these riddles and when I first learned of how JavaScript does these really weird things, my thought was that everything has an explanation. And my thought process was, okay, these are weird, But no matter how many times I run them, it's going to be deterministic. No matter how many times, if I know how the JavaScript interpreter works, I'll be able to tell you ahead of time and answer these riddles correctly every single time. And this isn't only for JavaScript and only for these stupid riddles. It's for every single bug we encounter. It's for every single thing we do in programming. I'm leaving AI out of this because that's a whole other story. But for just your basic programming, there are clear rules, sometimes less clear, but there are rules. Programming languages are code. So not only can we look into them and read the actual code that's running, but we can, if we know how code works and we understand how the structure works, then we're going to be able to understand how our code is executed in its environment. So in this case, we can actually, we know how JavaScript works because we know how code works. We know how the interpreter works because we know code. This is a better debugging mindset. A lot of the times when I'm debugging, if it's a really tough bug or, I don't know, I'm having a long day, I'll kind of feel exasperated. And I'll get to this point where I'm like, I have no idea where it is. I'm so tired of looking at this code again and again. Like, I'm getting nowhere. It's not bringing me anywhere. If I stop and say, well, wait, everything does have an explanation, though. This is code that I wrote, and I can dig in deeper. I can dig into the programming language. I can dig into the runtime. I can dig into the internals like I did in the JVM earlier. Because everything has an explanation. Everything will work the same thing every time. And with that more positive attitude, debugging actually becomes easier. And another interesting thing is that this kind of made me engage with the community more, because I wanted to know not only what was happening, which is maybe reading the source code, but also why. Why was something written a certain way? And an interesting thing is that a lot of people who are creating things in the open source world, or in general in tech, they write why they do stuff. And even when they don't write why, you can actually reach out and ask them, which is pretty cool. It's something I've done. And if I want to know the explanation, then that's what I'll do, and it'll make me a better developer, because I've spoken to some awesome people. I've read some good things online. So yeah, so everything has an explanation. Okay. Now with that, sometimes things are complex. Do you guys know this guy over here? Yeah, okay, cool. It's the Go Gopher. Basically, Go is a very strict language, right? Go tells you, if you don't know, in Go, if you want something public or exported, it has to start with a capital letter. And if you want it private, it has to start with like a small letter. And that's basically the whole story of Go in like one small example, where they're really, really strict. And I find it nice, because that means that even a project I don't know will be written in a way that I'm pretty familiar with already. But also, this should make things pretty simple, right? It was also built for readability. It's not C, so it's supposed to be more simple. But, however, I had to write some code in Go. I'll show it to you in a second. And I was tired, because a lot of times we kind of hear that if you're not able to explain it to a 5-year-old, then you don't know it well enough, right? Or you're not doing it simple enough. So this is the code that I wrote. It does something with windows. I barely remember. It's some calculation. You have a window, and then you have to calculate the percentage in the window, but then the window can move. Something like that. And basically, this small piece of code took me so long, and I kept trying to make it better and more readable. And I was like, someone should just be able to read the code and understand it. And you're trying to read the code, so do you understand it? No, okay, good. Thanks for the one brave person. Yeah, because sometimes things are just complex. So that code, I really don't believe I could have made it any easier. Things like algorithms, they're just going to be complex. You have to learn the algorithm. And even if you know the algorithm, then looking at the code and understanding what's going on there is a whole other story. Code that's optimized for performance, if the number of functions or the number of variables you use is dictated by your performance constraints, then that's going to be code that's not as easy to understand as you would like. And sometimes there's just complicated logic. There's things that are complicated. If you have like a 10 by 10 array matrix, it's going to be complicated, and there's nothing to do. Or there is something to do, but we have to, first of all, say, okay, it's okay. I wrote some complex code, but let's make it as easy as we can and then move on and not just continue with these iterations of trying to make it easier. So I kind of gathered some tips to make the complex code as least complex as it can be. Before you code, try to explain the problem and the solution to someone out loud. This will, first of all, it'll make you simplify it because explaining complex thing is complex. But it'll also have a new pair of eyes on the situation and they may be able to help you out. And you're also already mapping out how you're going to solve this when you're talking about it out loud. As you code, stick to coding conventions. Now, that's not only like, as I said, capital letter or small letter. That's not the most important part. The most important part, in my opinion, is to choosing a terminology and sticking with it. Because if you use create and generate and new in your code all throughout, then it's going to be really hard for someone who finally grasped at what generate means if the next time when you mean generate, you're going to say create. So if we stick to one terminology, once that, first term clicks, then the rest are just going to follow. So that's really important. We want it to limit abstractions. We love design patterns and generic code and all these things, but if your code is already complex, don't make it more complex by adding more code than it needs to be. So limit your abstractions, keep it as short as possible, and prefer small functions and short statements. Not always possible, as I said, if you have performance constraints, but if you can, small functions, have a layer of abstraction where you can just read function names and understand what's going on. And then if someone actually needs to see the implementation, they can look at the functions, which are also small, so they're also going to be easy to understand. After you code, you need to document why. Why is super important because a lot of the time what happens with complex code is someone will come and see your complex implementation and say, wait, I can do that much better. My code will be crystal clear and short and everything. And then they do it, and it's not crystal clear and short. It's just different, but it's not less complex in any way. But if you document the why, and if you say exactly why you did what you did, and that it cannot be simpler than that, then there's less chance of that happening. Also, you need to document the how. Does it work? And then the last step, which is really important, which is part of a feedback loop, have someone take the documentation and your code and have them understand what you did. Now, don't take the person that you already talked to about the problem and the solution with. You need someone else because otherwise you're kind of cheating, right? You want someone that doesn't know the problem, that doesn't know why you chose that solution to understand. They're probably going to have questions, so you should answer those questions in your code or your documentation. But this will make the most complex code as simple as it can be. Cool. So we have complex code. I think the next stage is to test it. And I wrote Ruby for a short amount of time. Ruby is interesting. Ruby is a language. Not many people use Ruby, but it has so many frameworks. And well, I'm talking to the Java community, so you guys have more, don't worry. But they also have a lot of frameworks and tools and stuff like that. And one of their frameworks is a testing framework called RSpec. And RSpec is interesting because it supports behavior-driven development. Basically, the idea is you can read the tests, and by reading the tests, you're supposed to understand what the code is supposed to do and how it's supposed to behave in certain situations. So I got an example here. Now, I don't want to teach you guys Ruby, but it's pretty self-explanatory. You have the first code block where you're describing fill gas. Fill gas means that you're testing the function fill gas. There's a typo there. And then we have 3 tests in that code block. The first test is testing that it should require 1 argument. Great, and then there's the test itself. It should also require a numeric argument. So it's going to test with a string argument, make sure it raises the right type of error. And then I'll go even further and say under the context where the gas tank is full, it shouldn't fill anymore. Now, just by reading plain English words without really understanding Ruby, we already know how the code is supposed to supposed to behave, we can pretty much also imagine how it's written out, which is really cool. I really love this about Ruby, about RSpec. Now, on one hand, you may be saying that it's more verbose, but on the other hand, we often encounter this issue where documentation doesn't fit the code, right? We've written documentation a while ago, we update the code, we don't update the documentation. This makes sure that the documentation and the code stays as valid as possible. Now, RSpec, I'm not coming and saying move to Ruby, move to RSpec. So I did gather some ways that I've improved my testing practices since learning RSpec. The first is to keep tests as small as possible. So like I said before, with small functions, small tests are also good. Usually I'll use nested tests for this. Just keep the test as minimal as possible. That way, if the test fails, you can clearly see what the issue was. Use parameterized tests. That's good because once you understand the logic of the test, then you can see all the different inputs and outputs and understand the behavior with that logic. Use a mocking framework. I think this one is really underrated, but if we have, so specifically our Java code, we've implemented a lot of the mocks ourselves. So we just create a class, have it implement the interface or the abstract class that we want to implement. And it's really tough for me when I come and try to read and understand these tests because I have to actually go into the mock, understand what it's doing, make sure there's no bugs in the mock itself, and then I can continue and read the test. And when using a mocking framework, well, it's meant for mocking, so they probably did a better job than someone that was just writing tests for their code. But also, you'll have consistency in your code. It'll look the same in every single place, and it'll usually be more expressive of what you're trying to do with that mock, which is, call this, collect that, return this inside the test itself, so you don't need to jump anywhere else. The last one I think might be a bit controversial, but it's to use a method chaining approach to testing utilities. And what that means is to have an object passed as the first parameter and returned. So basically you would have, call function dot return whatever dot once, for instance. So you'd have all these functions chained after one after the other. I did create a small Java example just to show how this can be done. Nested and display name, if I'm not mistaken, were introduced in JUnit 5. So you can use nested to create subtests. So just like I did the describe with fill gas, I'm just creating a class to test one specific function. And then I use the display name as I used the description in my RSpec tests, so should require a numeric argument, and I made sure that the test was really small. So now that we've got our tests in a row, we're going to find out pretty quickly that only production matters. So after moving on from Ruby, I'm ready to face Python. And Python is interesting because we had this code in Python that wasn't really performing that well, but what can I expect? It's Python. So what we thought to do was to increase the number of threads we were using, right? As many things in parallel as we could. But instead of getting more performant, it was getting less performant, and we were having more performance hits, and it was doing the opposite of what we wanted. And what we found out was that when we're using it on our machine, and we're, I don't know, maybe testing with a few requests at once, when we deploy it to production and there's a real number of users using, then it all goes downhill. And you may have thought that I would learn a bit about Python here, but what I learned was that only production matters. So something working on your machine is nice, that's cool, that's fun to play with, but in reality, if you're delivering code, if you're working for an organization, if you want people to use what you've created, the only thing that matters is how it works for them and how it works in production. For those of you interested in our Python problem, the reason was that Python has they call it a GIL, a global interpreter lock. So no matter how many threads I'm creating, it's only really running one at a time. And the more threads I was creating, they were just fighting over that lock instead of actually performing the tasks that they should have been performing. So, okay, now, since only production matters, I have gathered a few tips, as always, for how to make sure that production is doing just what our local machine is doing. So first of all, quick deployments. If you deploy quickly and often, then when issues do arise, you can clearly see which deployment caused that issue and narrow it down. Also, a fast feedback loop. Tests that run quickly. We had like a 2-hour session of a guy basically just telling us your tests need to be quick, and he was right. I don't know how to do that. I'll update you in the next in the next talk. But if you can get your tests to run quickly, then you're going to have much faster feedback. You're going to have developers that are much happier because they can clearly see what's going on, and you're going to have a faster feedback loop. And the third thing, not least important, is to monitor all environments. So usually we're going to push to staging or to a dev environment before we're pushing to production. A lot of times we're going to figure out problems at that stage. A lot of people don't monitor those environments. And if you don't monitor those environments, you're not going to know how to diagnose any issues, how to troubleshoot issues in those environments before they reach production. So important to monitor all environments. Now we're reaching kind of the last lesson. And I think this one is an inspiring one. So this is about C++. I'm not a big fan of C++. Are there big fans of C++? Okay, that's cool. There's a few. Good for you. I'm not. So yeah, C++ just has a bit too many keywords for me. It's very heavy on the learning. As I said, I'm just jumping between 7 different programming languages. I'm trying to find the minimum I have to know in order to develop for these projects. And C++ was never really meant or good for that. But I decided to view this in a positive light and to tell you that there's always more to learn. On the flip side, it might feel like you never know enough. Like it's a constant thing that we're all feeling, I think, I hope, where there's always something new. If it's a new framework, if it's a new tool, if it's, I don't know, a new project that you're working on, there's always something new, a new design pattern to use. There's always the next shiny new things, and it's okay not to know. You need to know enough. You don't need to know everything. Also, when you need it, you'll know. So this was my biggest friend with C++ because I was trying to learn it all. I was trying to learn all the keywords. And the issue is that you don't need to only learn the keywords and what their use is, but also how it actually connects with the code that you're writing and when to use them correctly, which was my biggest issue. But I kind of let that go and I said, okay, when I need the keyword friend, if you didn't know, there's a keyword called friend in C++. When I need the keyword friend, I'm sure I'll know. So I can leave it aside for now, and when I do need it, I'll use it, I'll learn about it. But for now, it's good to just push forward and start coding. This actually, I'm talking mostly about C++, but this was a good thing for all of the programming languages that I did, all of the projects, because if I would spend too much time trying to learn a new language or remember an old language that I've already kind of moved past, then I would not be able to do my job as I'm doing it today. Also, software is always evolving. So this is back to the, you never know enough. You're never going to know everything. Software is always evolving. Choose what you want to know, what interests you, and go with that. So the last thing that I wanted to say, which is something, I did talk about Java a little bit here and there, but I think this is the main thing that Java taught me. It's a little cheesy, especially since I'm at a Java conference, but I like to call it community-driven development, which is don't reinvent the wheel, first of all. So many people have done so many things in Java that most probably are going to find your answers online. If you don't find your answer online, ask for help. Maybe there's someone who did that, who does something similar, but they haven't just published anything, but they can help you out pretty easily. It'll take much less time, and you'll maybe gain a friend. And then the most important thing is that once you do get your answer, or once you have invented the wheel for something that no one's invented the wheel yet for, share back with the community, speak at conferences, write a blog post, create an open source tool. That's community-driven development. We're all better developers when we develop together. So thank you, first of all. And then I think the last thing I want to leave you with, just so you're not like, oh, she was super nice. No. So this is my last JavaScript riddle. um, yeah. So this is 6 symbols, and apparently in JavaScript you can write anything out of 6 symbols, which is pretty cool. If you want to check it out, that's the website that will do that for you. Yeah. And now thank you for real.